So from what I understand, your paper, Alessandro, is about artificial intelligence used on Sentinel-1 data to detect points.
Actually, I prefer natural intelligence.
I can give you the...
yes. Can you hear me? Yeah.
You are happy with this one, then...
Okay, great. So thank you.
Yeah,
so no, I'm not going to speak about artificial intelligence because it's something for sure everyone will take advantage of in the next few months, probably. But I will simply try to go back on INSAR because probably it's the only thing I can speak about. And indeed, when you look at the number of publications, where we saw this morning, the growing number of publications about land subsidence, and this is a very similar graph concerning the word INSAR. And indeed, it's just a way of saying that it's probably worth that we discuss about INSAR in this conference, because it's a way of look at land subsidence and get hopefully some good data. And indeed, INSAR is gaining momentum. And why? To me, one of the key points is that INSAR is a multi-scale technology. So you can go from very local analysis, for example, you want to know whether or not a certain section of the Milano Duomo is moving, up to continental scale. And the EGMS indeed is the first project where indeed was possible to get information all over Europe. Now, thinking of the projects I've been involved in, this is not the full list of nations where you have a national INSAR databases. Of course, you have the Netherlands, you have Germany, you have Greece, we have just completed Austria, so there are many others. But indeed, if we look at the trend, we could see really a quite sharp acceleration over the next 4-5 years, thanks to the launch of the Sentinel-1 constellation, of course. That was a very extremely important moment. And thinking about the GMS, I'm not going to really speak only about the European Ground Motion Service, but it's important that we share some basic facts. Now it's the first INSAR database at continental scale at full resolutions, because previously there were a few publications about European ground motion data, but not at full resolution. And we process all Sentinel-1 A, B acquired over Europe, and this is very important. I'm going to speak a little bit more about it. All data were calibrated using a GNSS model, because once again, and I will go back to this many times over the talk, I really think GNSS, GPS, in-situ observations and INSAR should really work together. INSAR people should not oversell the technology. On the other hand, people used to in-situ measurements should try to look up and remember that there are also satellite data that sometimes can be extremely useful. Was possible to develop this was on the Norwegian partners involved in GMS, was possible to develop an easy-to-use web platform, and there are 3 levels of products, and this is getting quite common. You have the raw INSAR data, so line of sight data with a local reference. Then you have fully calibrated line of sight data, calibrated with the GNSS, and then you have vertical and east-west time series, always calibrated with the GNSS model. So this data is useful for getting synoptic views over very wide areas, and it's somewhat unique what you can get with INSAR. In particular, whenever you need to to map landslides, no, over very large areas. And then, of course, for all those colored dots, we get a time series along the line of sight. But then by properly combining ascending and descending, and hopefully getting some information about north-south, you can retrieve vertical and east-west information. So it's good because you can go for very wide areas and immediately spot where you have some issues, say. And it's not a panacea for all kind of diseases, because indeed, if we are getting to these kind of results, Sentinel-1, medium resolution, nice, okay, but if I need to get the most about a certain village, for example, there are other information sources. And we shouldn't really forget about the fact that Sentinel-1 is great, is wonderful, but it's not the answer to all possible INSAR applications. I don't think we have a silver bullet for INSAR applications. And indeed, we are playing now with not only YALOS-2, but also SAOCOM data, and next year we should have access also to NISAR, the US SAR missions data. And it's very important to keep in mind that you can have very different penetration, for example, in vegetation, whenever you play with different frequency bands. So it's a starting point, yes. For sure, providing annual updates as for EGMS is not enough for fast deformation phenomena. So it's not the right tool, in my opinion, for looking into individual buildings or very small areas. With L-band data, you can better penetrate canopy and get more information about vegetation. And is still a nice project. The GMS is something, to me, again, is a starting point. It's something which should help people being more and more aware about the potential of INSAR technologies. And also to see and appreciate the importance of fully calibrated INSAR data. And in general terms, I think, I've been working on INSAR for more than 25 years. Now I just realized, Ramon, that we met in Seattle, was IGAR's 1998, so 25 years ago. So, and indeed, I still think it's different when you process data over, say, a few hundred square kilometers, and whenever you want to go for the whole European INSAR database. You have constraints, you have a different impact in terms of atmospheric effects, you need to come up with the best mosaicing strategies. The computational burden is extremely different. Now we rely more and more on cloud computing, and the cost can be crazy in terms of cloud computing. But also in terms of quality checks, the kind of checks you can do feasible for small areas is completely different, of course, compared to what is feasible for the whole European database with about something like 6 billion points. Last but not least, again, we are really seeing the importance of having access to some good, possibly GNSS model. Because whenever you can calibrate INSAR, first of all, you get something easier for user to compare and integrate with other data sources. For example, again, GPS or say also total stations. So in general, you get a better estimation of vertical and east-west components because you are properly considering also the impact of north-south displacements. And in general, okay, you can try to mitigate edge effects, because mosaicing is not a trivial task to perform, in particular in AGMS. And so it's very important to remember that if you have access to low resolution a priori information, everything gets easier. And of course, the generation of a database of measurement is much easier to compare with other data once you have calibrated in SAR. So in terms of caveats, I've already mentioned this. Sometimes the data you can rely on is not enough. In case of EGMS, we are starting from a velocity model with a 50-kilometer posting. Sometimes it's good, sometimes it's not enough. And sometimes a velocity model is not enough because the motion is extremely non-linear. So, for example, in very actively seismic areas, it's not enough to rely on velocity model. And this is California. We've been serving the Department of Water Resources now for a few years. And indeed, in this case, was extremely important to get high quality GPS data. The final goal was just the vertical displacement, not east-west or north-south, but still was important to reproject, of course, 3D GNSS data along the satellite line of sight. And indeed, it was possible to have also a validation. In this case, the motion is far from linear, and still was possible to get this nice figure, less than 6 millimeters, with 95% confidence. And so, where are we going? In my opinion, there are some trends we see already for INSAR. On the one hand, we have these national databases, and I'm sure all of you will get familiar with them, and we will try to take advantage of this data, typically updated every year. So we will have international or national space agencies investing in SAR data, and we will have very wide areas covered by means of these expensive machines, because still it's something costing a few €100 million each. And then we have a second trend, a quest for cheap sensors and very fast, short repeat cycles, so frequent updates. And these are the typical projects also private corporations are pushing for. So there is a growing number of commercial projects for monitoring very local areas. And so you see, we will have both medium resolution data and very high resolution with short repeat cycles. And the companies like Capella Space, Umbra Lab, ISI, I'm sure some of you are aware of these new companies, and are all pushing for this kind of applications. And then in terms of frequency of updates, of course, annual updates is not enough. And also people working on landslide monitoring are asking for a continuous update of the information. And this is what we are trying to do, in particular for some regional governments in Italy. Now, in terms of use of artificial intelligence, indeed, machine learning approaches are playing a key role for the identification of anomaly. So suppose you have 1 billion points. Okay, you should identify what's going on over a certain area and immediately say a word or a warning to decision makers. Okay, in this case, you are looking for something like this. So a change in trend in the time series. And this is indeed possible, not only thanks to, say, the conventional approach based on statistics, but also something more, say, trendy these days based on machine learning technologies. So, coming to the conclusions of this talk, for sure, surface deformation phenomena can be mapped routinely on a national and even continental scale with SAR data. And we should always keep in mind the peculiarities of wide area mapping compared to conventional in SAR. Conventional in SAR, I mean, when you want to process data over a city, not over, say, the whole nation. And also, we shouldn't be afraid of calibrating in SAR data. Typically, the number of permanent GNSS stations is growing steadily, in particular in Europe, California, Japan, and not always those areas. So let's try to work together with people expert of GPS and GNSS, and calibrated in SAR data can allow users to obtain synoptic view of subsidence, and data screening tools are becoming extremely important for data browsing. And indeed, let's try to keep in mind that wide area processing is good, Sentinel-1 data is good, but you can get something else based on different information sources like high resolution X-band sensors or L-band missions like ALOS-2, SAOCOM, and in the future, NISAR. So thank you for your attention.
Thank you, Alessandro. Questions? It was very clear. Huh? We got a lot of advices.
Okay. Zong, probably one. Huh?
Yes.
Well, Alessandro, thank you for this always very visionary talk. So I'd like to hear your comments. I think the integration of INSAR and GPS is absolutely great. But can you talk about what is difficult? I mean, INSAR might from particularly reference system, GPS is common. So what are the the things I should consider in terms of integrated GPS and INSAR?
But I mean, first of all, it's something related to geometry. I remember also a couple of talks by Ramon and the students. So when we combine ascending and descending data and we say, okay, we can estimate vertical and east-west displacement, I mean, as soon as you have a strong north-south displacement, this can create a sort of bias on the estimation. So typically, you have access to some prior information, and GPS can play a role in this. Then, of course, GPS is important because even though you have sometimes cycle slips, similar to phasor wrapping, but I would say it's more rare. So you have something you can use to anchor your data. And finally, can be used also to compare sometimes the estimation of your atmospheric phase screen with those you get from GPS. So it's a quite complex, topic, to discuss. But for sure, both technologies should be used together. Yeah.
Thank you. Another question? No. Then thank you, Alessandro. And we are going to upload the social